Look closely at this industrial feed mixer. It is completely packed with material right up to the rim. If you're running a feed mill that's behind schedule, this looks like a brilliant hack. By stuffing extra material into every load, you can completely eliminate an entire batch cycle from the day's schedule. The machine is running, the feed physically fits inside, but the resulting ration coming out of this mixer is going to be completely compromised. The mistake is treating the mixer like a static storage bin. The storage bin's only job is to hold material. A mixer is a dynamic piece of processing equipment engineered specifically to move it. When operators look inside an overloaded machine, they see the augers rotating and assume the feed must be mixing. But mechanical rotation only proves the motor has power. It doesn't prove the material is actually circulating. Because that feed is not circulating properly, ration quality drops. Discharge times drag out. And mechanical drives burn out. So we have to ask, why does throwing the available space inside a steel box actively destroy its ability to do its job? To understand what happens inside the mixing chamber, we have to stop looking at the scale. Weight is critical for formulating a recipe, but it tells us almost nothing about the physical volume that feed will actually occupy. Look at this comparison. On the left, we have 1 metric ton of dense processed grain. On the right, we have exactly 1 metric ton of chopped roughage. They exert the exact same downward force on a load cell, but roughage takes up substantially more space. This difference is bulk density. Chopped hay's physical structure creates massive air gaps, meaning you need a much larger physical footprint for the exact same mass. Because cattle rations contain these highly variable ingredients, the volume of a standard batch can change overnight. If your hay supplier drops off a load of forage that is slightly drier and fluffier than usual, your normal 5-ton recipe will suddenly ride significantly higher inside the mixer. Equal weight on a scale definitively does not equal physical fill inside the mixing chamber. Inside the machine, ingredients need room to circulate. They have to fold, lift, and tumble along precise pathways designed by engineers. When operators pile material high above the manufacturer's intended working limit, they consume the open airspace required for that tumbling action. This cross-section shows exactly what happens as the feed breaches the top threshold. The overloaded material physically chokes the circulation pathways. Ingredients lock into place, forming stagnant dead zones where no actual mixing occurs. Pushing solid steel augers through compacted, unmoving feed forces the machine to work against intense resistance. That places severe grinding stress directly onto gearboxes, hydraulic systems, and drive shafts. You might think you can solve this by simply leaving the mixer on for another 10 minutes. But if the material can't physically fold and circulate, extra time won't fix the distribution problem. Maxing out the physical capacity actively chokes the machine's effective working capacity. It degrades the uniformity of the cattle feed and accelerates wear and tear on expensive equipment. If overloading is the problem, you might assume that running a nearly empty, extremely small batch would yield a perfect mix. But a tiny volume of material lacks the critical mass needed to properly engage with the augers or paddles. Instead of traveling through the normal circulation pathways, the ingredients can easily slip under the components and fail to distribute evenly. Reliable processing only happens within a specific, validated working window. The geometry of the machine fails if it is stuffed to the brim, and it fails if it is practically empty. This process is a sequence of physics. It starts with an ingredient's physical properties. These dictate bulk density, determining total batch volume. Batch volume dictates actual fill level. Fill level governs material movement, ultimately deciding final ration uniformity. Ignoring a single step guarantees failure downstream. You cannot separate the physical characteristics of the feed from the mechanical performance of the mixer, which brings us back to that operator trying to save time. Eliminating a loading cycle by overfilling the machine creates a dangerous illusion of efficiency. On paper, you save minutes by cutting a batch. In reality, you spend that time fighting delayed discharges, paying for mechanical wear, and feeding inconsistent rations that compromise cattle performance. True operational optimization is about finding the best combination of feed quality and equipment reliability. It is never about sheer physical volume. We have to stop measuring how much a machine can physically hold and start measuring how much it can correctly mix.